Hi, guys. Can I get a sound check?
Hi, Professor. I can hear you.
Okay, great. Thanks. So I'm just trying to get organized here. Let's see. So better. Slide deck 3. Slide deck 3. Did I put a slide deck 3 in the? Do you guys have a slide deck 3 in your Zoom? Sorry. So in the files. Yeah.
I see a slide deck 3.
Yeah. That's good. Let's see if I have it. Oh, what am I doing? I'm just sitting here. What's it doing? Oh, I see what I'm doing. Sorry, guys. Let's see, slide deck 3. Okay, this is what I'm looking for. So I guess I just don't have it in my. I have it with my notes, but I don't have it as a blank. Sorry, guys. That's original. I have one. Sorry, guys. So a little dirty, messed up, but hopefully it won't be too distracting. To see my notes here. Okay, guys. So maybe I'll just end up erasing these things as I go, because let's see, what do I want to do here to make this less confusing? Let's see. Slides with notes. So maybe I'll just, sorry guys, I'll just go ahead and can I erase these or no? No, it doesn't even let me erase them. So sorry guys, I'll just use this. Hopefully you won't find it too distracting. I'll just make notes on top of notes here. Okay, so today we're going to be talking about how to make a silicon wafer. So let me take a step back first. So I'm assuming you guys have seen, MOS transistors before, but let's just do a quick review here. So MOS transistors, MOS stands for metal oxide semiconductor transistor. And there's two types of MOS transistors. There is the so-called NMOS, and then there is a PMOS transistor. Okay, so the NMOS looks like there is a N-type substrate, and then you put a piece of oxide, so silicon dioxide, on a region of this N-type material. So N-type materials, they have a lot of electrons floating around as carriers. Or I'm hoping this stuff is sort of familiar somewhat from some of your previous classes. Is this absolutely new to anybody? No. Okay, good. Well, anyway, so this is silicon dioxide. Then we've got a let's see, what's another color here? We've got, this would be some polysilicon. So this is initially when they first ended up making these MOS transistors, instead of polysilicon back in the day, this was some kind of a metal, aluminum or something. So the name stuck. So this is the metal. So this is the metal. The silicon dioxide is the oxide. And then the semiconductor is this sort of the N-type. Okay, so metal oxide semiconductor transistor. And the NMOS has, N-type substrate. And to actually get a contact to this thing, you would have two P-type stuff, and you make these P plus, meaning like highly doped P, so you can get a good electrical connection to these. Okay, so this point is called the gate. This point is called the source, and this point is called the drain. And the schematic for this looks like this guy, with this being the gate, this being the drain, this being the source. Okay, and we'll go in a few lectures, we'll sort of do a fuller review of this, but I just wanted to kind of remind you guys of what the structure looks like. And then at P-type, so in this class, in a real simplified view of using this as a switch, it's much more complicated than this, like voltage for current characteristics. But if you think of it as just a switch, if you think of this, again, really, really simplified view, which we'll start with, is if you put a positive voltage on the gate, you turn this guy on. So this looks like a kind of a switch being controlled by the gate. But as for this lecture, what I'm trying to show you guys is that this is kind of the structure you want to make. You want to have a gate, you want to have this oxide, you want to have an N-type substrate, and you want to have some connections for the source and drain, which are these P plus So this would be an NMOS. And then a PMOS, so NMOS, PMOS, which is the other type. It looks exactly the same, except the substrate is P-type. And you still have the oxide or silicon dioxide. And you still have the metal gate, which is polysilicon. And then you need to, instead of the N plus contacts, now you have, sorry, the P plus contacts, you have N plus. And now this is the source drain gate. And then this guy, the symbol for this guy is, put a circle on the gate. So gate, drain, source. And then the way to look at this is, again, this is sort of gate bar, I guess is the way to look at it. So if you put a negative voltage on the gate, we'll figure out, we'll see what that means. You'll get this guy to turn on. So a positive, say a positive voltage or a 1 will turn on the NMOS, as if you think of it as really a binary thing. And a 0 will turn on the PMOS. And, we're going to get into the weeds here, but at the moment, that's, again, I just want to have you guys just remember the structures we're trying to get here. And CMOS, which is what we're trying to get to, all this VLSI circuits are so-called CMOS, which stands for complementary metal oxide semiconductor, means that in the same silicon device, you have both NMOS and PMOS devices to have this. So that's what the CMOS stands for, is complementary. You have N and you have P, and it ends up that the logic circuits you can make having both the N and the P are very, it's like gives you some really nice functionality as a logic gate. So the history of this stuff was, when this stuff started, first they only had NMOS transistors in a wafer. That was called the NMOS technology. And that was, again, where things started back in, I think in maybe the 60s, 70s kind of thing. And it had some it had some good functionality, but there were some issues which we'll kind of get into. And so some smart person figured out, if you put in PMOS transistors as well, to go from NMOS to CMOS technology, you get some real big advantage in terms of logical functionality. Anyway, so now the problem that the factories have, which we're going to talk about, is to somehow get both of these devices on a silicon wafer, and not just on the same wafer and not just on the same chip, but you want them potentially adjacent to each other, because even at the case of individual gates, so if I was going to look at, say, a NAND gate, that's the symbol for a NAND gate, and sort of the functionality is something like that. So you have so this would be A, B, and out. It's a NAND gate. And if I was going to draw you guys the circuit for this NAND gate, CMOS logic NAND gate has 2 P MOSFETs and 2 N MOSFETs, where they're sort of paired up, where the gates are connected, and this is the out. So on a piece of silicon, not only do I have both N MOSFETs and P MOSFETs, but they're just sitting right next to each other. So that's what the factory is trying to make. So if you look at, so this is like so I drew, this is like sort of a little cartoon cross sections of what these devices look like. The real product looks like something like this. So again, I'm sorry, this looks kind of messy, but this is, oh, sorry guys, I totally screwed this up. So this should be P-type. And these are N pluses, sorry. And this is N-type, and these are P pluses. So I reversed NMOS and PMOS. So if you look at a NMOS, it's sitting on a P minus substrate here. And there are these N plus, like instead of having, there's no, so let me take a step back, sorry. So this is a wafer. So this is like, if you look at a wafer, you got this 12-inch, I don't know if you guys can see my picture here, but I'm holding like what looks like making a shape like a pizza, like a large pizza or something like that. Is that wafers we were looking at in the videos. So that's the top view. If you look at a circular piece of silicon, so if I'm looking at this picture, if I look at it from the top, it looks like the circular wafer that's 12 inches in diameter. But if I look at it from the cross section, so if I cut across that wafer somehow with a saw and look at it edgewise, which is this view, I see something that's about 1 millimeter thick. Okay, but all the devices, all the NMOS transistors, all the PMOS transistors, everything is just bunched up at the surface, because the way this device is made is most of the wafer is, you have to start with this wafer, and you can only put stuff on this thing to, implant donors, acceptors. You can build a device, you can, build the oxides and stuff on top of this wafer. You can't build it throughout the wafer. So all the stuff, all the transistors, all the business end of the stuff is bunched up in the very top 3 to 10 micron. By micron, so, and this is something you'll hear a lot, is micron is micrometer, or 10 to the minus 6 meter. Okay, so that's a typical distance. So you'll hear about microns, you'll hear nanometers. Those are most of the numbers we'll hear about in terms of distances. So if this is the full wafer thickness, the full wafer thickness is very typically 750 microns. So it's I said 1 millimeter here, but it's really 750 micrometers, give or take 10 micrometers or something like that. And all that thickness does is it's really sort of a mechanical, gives, if you just had a 10 micron thick piece of silicon that's a centimeter on the side, it would be flop around. It'd be like thinner than a piece of paper and would flip around and break and etc. So all this millimeter or 750 micron, this substrate thickness does for you is it just makes it mechanically rigid so you can work with it. Okay, but all the transistors, all the connections between the transistors are all bunched up in the very top layer of this wafer. Okay, everything's on top, and all the positions, all the implants, all the stuff is happening from the top down. So those wafers are sitting, looking up at the equipment, okay, and they're getting worked on from the top. So for example, in this NMOS transistor, our gate and oxide are sitting here, but instead of this whole area being N plus for the source drain contacts, the contacts are only just on the very top surface. Okay, so the whole operation of the transistor is really sort of very narrowly close to the top surface. Okay, and so the silicon wafer itself very typically ends up being a p-type substrate, so you can make the NMOS transistors right on the substrate. Okay, because so this is get the p minus. Now, because you also need PMOS transistors in there, you've got a problem because the PMOS substrate is n-type. So what they do is they built in so-called wells in this p minus material. So they implant donors in this so-called well. So they changed the substrate for the PMOSFETs to be n-type by putting this, creating this area of n-type inside on top of this, on top of this layer. And then you put your P plus contacts on the surface. So again, if you look at this, you'll see that these are metal lines coming in to make contact with the source. This looks like a metal making contact with the drain. So this is like polysilicon. And let's see. And what was I going to say about this guy? Anything else? Okay. And so, another thing that this tells us, so again, very typically the NMOS transistors are sitting in the substrate, and to get PMOS transistors in the same substrate, you would have to put in a well, okay, and put the PMOS transistors in there to isolate them from the NMOS transistors and give them the right substrate. But another thing that this tells you or forces you into, as we'll see, is there's certain allowable voltages for the NMOS and the PMOS to make sure that the PMOS stays isolated from the substrate. Okay, notice that we've got this guy sitting in an N well. So as long as this N well is higher voltage than the P substrate, there's a reverse bias junction here between this guy and between the well and the substrate, we want this to be a reverse bias junction because you want to isolate this well electrically from the substrate. So you want this N well, N-type material, you want it to be a higher voltage than the substrate to make sure that it's reverse bias and it's isolated. Otherwise, things are going to short together and nothing's going to work. So as we'll see, that gives us a certain range of permissible voltages for the NMOS and a certain range of permissible voltages for the PMOS because they just have to share the substrate together. Okay, so this is at a very high level overviewing it. So in more of a cartoonish way, again, I'm sorry about all this drawings here, but this is what it looks like that the p-type, I guess this is really saying the same thing, except, you have the transistors here. Okay, so this is the PMOS transistor sitting on a well, and this is the NMOS transistor. Sometimes the NMOS transistor is put into a P well, sometimes not. And the reason there's a P well here, as opposed to just a substrate, is it allows you to exactly tune the potential here. It allows you to tune exactly what the threshold of this transistor will look like, etc. But the upshot is everything is bunched up very close to the surface up here. Okay. Additionally to that, you need you need certain amount of isolation. So this is oxide. Everything yellow here is silicon dioxide. Okay, you need to isolate physically the transistors from each other, even though through the substrate, they're isolated from each other, but sitting next to each other, you need to sort of further isolate them from each other, and you put them, you put various isolation things in there. Then you deposit metal lines to connect up. Sort of, this is a metal line that's connecting up to the source. And then as you have different metal lines, you need to put in isolation between those metal lines also. So you don't want this guy, for example. In this particular case, the drawing doesn't really show it because this is a short between this metal layer and this metal layer through here. But sometimes you want to have a metal layer up here that's not connected to the metal layer here. So you can't have it just be sitting on top. You need to have alternative layers of metal, oxide, metal, oxide with via connections between them where you draw them to get connectivity. Okay. So what you end up having to do when you're building, you want to build this thing up. So what does building this thing up look like? You're going to go through a bunch of processes of implanting. When you're building the transistors, for the most part, you're implanting N plus, P plus regions, etc., into the silicon. So you're putting donors and acceptors in different parts of the silicon, and you're taking it through temperature cycles. And because you want those different, so you want N plus here, but you want P plus here. So basically what you do is you go through these processes where you end up masking part of the silicon. So you end up masking, let's say you end up masking this area and this area, and on this area you put in N plus, so you end up with N plus here, and you don't end up with it over here, and vice versa. So you go through a bunch of steps of, so this is like sort of the very high level steps, is you end up creating these regions where the transistors will be placed. So these are trenches, so-called trenches, that are separating the transistors from each other. Okay, and then you go through and you implant these wells, whether you have N well and P well or just N well, you implant those. Then you put in the polysilicon layer for the gates. It turns out that you actually put the polysilicon layer for the gate first, and then after that you put the source and drain implants, and then you start creating contacts and then putting in the metal layers. Okay, so sort of up to here, it's all happening in the silicon, and after this it's all happening on top of the silicon. So everything here is happening here in the silicon, and anything above this is sitting on top of the silicon. It's all still very thin. So this, this distance, like I said, was maybe like 3 to 10 microns, and then this distance is another 3 to 5 microns or something like that. So it's all happening at the very much top, but this is all things you're doing to the silicon. You're putting in N plus, P plus, etching the silicon, etc. And here is where you're putting stuff on top of the silicon in the form of the metallization layers. Okay, so that's at the very high level. So to do this repeated process of patterning, so each one you're creating these patterns of doing these implants, because you want to define the transistors in different areas with different sizes, with different connectivity. So to do these different patterns, this patterning is called a lithography process. So in a lithography process, you end up with, so what you end up having is you need a mask. You end up, let's say if I wanted to work on part of this silicon, and I think this lithography is like generic. I'm not, it's a general, sort of a generic printing process. So I think, whether you're building some types of pictures or making a printed circuit board, et cetera, these are all sort of similar ideas. And the idea is that, let's say I want N plus in some part of the silicon. Okay. What I'll do is I will put some spin on some material here. And so this is something called a so-called photoresist. And the reason, we'll see why it's called photoresist. So it's like kind of like an organic material. When you're putting it on the silicon, it just looks like a liquid, looks like a thick sort of syrupy liquid. Okay, but it's very much a liquid. And the way you put it on is through spin coating. So, the equipment is actually pretty advanced, but what it ends up being is you've got the silicon wafer, it's sitting on a stage, and you put in a very small amount of this photoresist material. That's again the syrupy liquid in the center of the wafer. And then this wafer sitting on the stage starts spinning very symmetrically, very uniformly, et cetera. And this spin coating basically spreads this photoresist material evenly across the silicon. So, and it spreads it into a film that's maybe, again, I don't know how thick that film is, let's say about a micron thin film, but spread uniformly across your wafer. Okay. So that's, you're putting it on. And then the next step you make is you take your mask and you put your mask plus the wafer in a so-called, put them in a so-called lithography machine. And the lithography machines are the most expensive machines in a fabrication facility. So the mask, so the mask looks like a big glass plate with chrome patterns on it. So a mask, again, looks like a big plate, which is like very optically flat. You need it to be a high quality glass plate, and you've put in some chrome patterns on there. The chrome is an opaque material. So if I look at the glass or this mask here, looks like where there's chrome. So let's say this is the glass. Okay, it's not touching the photoresist or the wafer, but where there's chrome, I have, so these are chromes. These are opaque regions. Okay, then I'm going to shine some kind of, typically an ultraviolet light on this whole thing. Once the reason this lithography equipment is so expensive is I'm not drawing a very, very complex, a very large lens or optical elements that are basically imaging these directly on this. And sort of, if I've been to places that actually make lithography machines, like in their museums and showrooms. So the lens elements look like, they're about the size of a fridge. So these are very, very precise. And that, remember, they're printing, we're printing 3 nanometer, 5 nanometer features from the mask onto this photoresist. So we want to basically sort of illuminate, have this shadow of these chromes or this image of these chrome pieces appear on this photoresist. But they're these could be, these distances, or we're talking about 3 nanometers, 5 nanometers. And those of you guys may have studied optics might be wondering how the hell they do this, because you typically have a hard time imaging at lower resolutions than the wavelength that you're using for the imaging. So even ultraviolet light is at whatever 200 to 300 nanometers, whatever it is, maybe it's 100 nanometers, but just the wavelength of the light is much bigger, much bigger than the features you're printing. So it gives you an imagination about the kind of tricks they use. There's like lots of tricks. So it's a very expensive. I'm just showing you guys at a real cartoon stage.
Professor.
Yeah. Mohammed.
So the mask is just a generic glass plate with some chrome pattern, right?
Yeah, but I mean, generic. I mean, it's a very expensive, very flat, very transparent, very low defect piece of glass.
Mm-hmm.
And those chrome patterns on there are also similarly very low defect, very fine featured, etc. So if you look at the actual mask set, so there's a bunch of steps that you're doing, like maybe 100 steps or something to actually create the full wafer, the full end product. And so say for a 65 nanometer process, you might have something like 50 plus masks to define all these different features. We'll see like the steps you'll have to go through. And all of these mask sets, so if all these masks might end up costing you, for a 65 nanometer process, they might cost, $300,000 to $500,000. So my point being that when you say generic, I just wanted to make sure they're really high optical quality, but it's just glass. So it's not like it's stuff that's, I mean, it still has to be transparent in the UV. So you just have to make sure it's the type of glass that still stays transparent in the UV and all that stuff. But besides, it's not like really anything special.
Expensive.
It's very expensive, yeah. And it just gets the price. 65 nanometer is still lagging technology. I mean, you're talking about 3 nanometers right now. So, those, I don't even know what those masks cost. You're talking about, $10 million plus mask sets. Does that answer your question, Mohammed?
Thank you, Professor.
Sure. So again, in this simplified view, so now what you're doing is you have, using this mask and this lithography machine, you are basically exposing parts of this photoresist that you spun earlier on this material to the light, and some parts not. So let's say, again, in the cartoon drawing, let's say, let's pick a good color. So this part, oops, this part that's in this gap area gets exposed to the UV light, and these parts don't. And then again, this part gets exposed to UV light, and these parts don't, and so on. So let me just draw again. This is all a cartoon. So now you have, again, this photoresist gets these parts get exposed to the UV light. Okay. Now there's different kinds of photoresist, but this photo in this resist, the photo in the photoresist means this material, that's the syrupy liquid, organic syrupy liquid, is responsive to light in the sense that something happens in the photoresist regions that get exposed to light. Something happens to their polymer chains. I don't know. It's all for the chemists, but something happens there. Okay. Now, either it gets hardened. That means this part goes from being a syrupy liquid to almost a solid. Okay. Imagine maybe a syrup that's been sitting there in your table for a long time and gets sort of hardened, or vice versa. But let's, for the sake of discussion, say this stuff gets hardened. So this green stuff, because it got exposed to light, gets hardened. And this other area over here that didn't get exposed to the UV light because of the mask is still a syrupy liquid. Okay, so all right, so now you take the wafer out of the lithography equipment, and then you do a so-called cure step. So this was expose. So step one was expose the photoresist. Then you do a cure, which is just you put the stuff in this wafer with this resist and everything, you put it into an oven, you heat it up, not very much, but enough that this stuff really kind of sets to some extent, but not too much, I guess. And then you go through a process called, there's just different names for this, but you can call it lift off. There's different processes, but it's a chemical wet process. So now you dip this wafer, or really spin on this wafer some other material that basically removes the resist that's not hardened, but leaves the resist that is hardened. Okay, so the resist that's hardened through the cure and exposure stays on. So if I was gonna, hopefully I can do this without causing a lot of problems. So this stuff that didn't get hardened gets removed. So let me remove this stuff. So now this is not in the we're not dealing with the mask anymore. This is sitting outside, and this goes away. So you end up with your this is your silicon, and these are the hardened photoresist areas. Okay, so now this acts as these hardened areas act as a kind of a mask. So these act as a mask. So these are in some ways an imprint of the actual glass chrome mask, okay, on your silicon. Now, if I put this in an ion implanter and implant the whole wafer, so I'm implanting the whole wafer with, say, for the sake of discussion, let's say I'm implanting the whole wafer with N+. Okay, this, where there is the hardened photoresist, that N+ ions, they don't have enough energy to go through to the silicon. But where there is no hardened photoresist, they'll go into the silicon. So what I'll end up with is N+ in these regions. Although I've got the whole wafer is getting implanted, but these photoresist, these hardened photoresist material is creating this pattern of N+s only where there is no photoresist. Okay, so for the sake of discussion, let's say these were my N wells, where my PMOS transistors were going to go. So the way I define those N wells is, put this photoresist on, I implant it, and then, so now I got N+ where I want it, my wells where I want it. Then I go through this process, which I'm going to strip the photoresist. So again, this is a chemical process where you give it a chemical that doesn't care if this photoresist is hardened or not. It's still not hardened like rock solid. It's again, it's sort of I don't know if you want to think of it as a like a liquidy solid or a solidy liquid. I don't know which one look at it, but it's still not so set that no chemical can remove it. So the second type of chemical, you can actually remove even this hardened photoresist. Okay. And so now I have this N plus in this. Okay. Now let's say for whatever reason, I wanted to put a P plus connection on these things. And now I do the process over again, except I spin another photoresist layer on top. So I go through the whole process again. So I do N plus, so sorry, I put in photoresist on top. I put in another mask. Let's say this mask is for putting in contacts for this N plus. So the mask would be, sorry, consistent drawing. So this is the mask. This is a piece of glass. Now it has copper everywhere except some small gaps here. And now let's say I expose this again with UV light through these holes, and then I only harden this area, this area, this area, and I do the cure and all that stuff. So I'm like just going through the process, and I take this out of the lithography machine. I strip this stuff away. Sorry, I did this the wrong way. I wanted to only have openings. Let me excuse my thing. So just imagine I did that the correct way, and I ended up with photoresist everywhere except those gaps. Okay, and now I go through and I implant P plus everywhere. Okay, so now I end up with P plus only in these areas. And then I go through and strip this resist away. And now I have an N well, or I have N wells where I want them, and I have these contacts to these N wells, so I can, you know, whatever, or source, you know, source drains on these N wells. Okay, so it's this sort of repeated pattern of going through. So this is, sorry again for the crummy looking notes here, but you end up going through this process of doing the photoresist coating, using a mask to expose the light, developing the photoresist, etching the photoresist, and then doing the whatever process you're going to do, whether it's an implant, it's oxide growth, metal deposition, then removing the photoresist, and sort of doing this over and over again. And you might do this process over and over again, might take like, you know, you might do 100 steps. And so the masks are expensive. So what the factories do, so let's say you have 100 steps in your process, or 120 or 100 or 200 steps. What the masks are very, very expensive. So the foundry engineers, what they do is they use the same mask for multiple steps. So for example, they use some masks that and then they use a different type of photoresist for the same mask. In one type of mask, the photoresist gets removed where there's the chrome, and with the same mask, they use it for another area. They use the same mask, but the photoresist stays with the chrome, etc. So a lot of what the factory people, the engineers that are creating this manufacturing process, they have a few tools to work with. They can create basically these masks and do the photoresist hardening, etc. They can etch the silicon. They can deposit donors or acceptors or N or P type dopants into the silicon at different energies, which means, and different concentrations, which means you can get higher values of N or higher values of P, and you can get them at different depths. Higher energy puts it at a deeper depth in silicon, and lower energy puts it closer to the surface. And the different concentration gives you, we can put either like an N plus, which is a lot of N, or N minus, which is not so much. So you can have those tools. And then you can deposit oxide and deposit metals and pattern. So a lot of what the fab engineers do, or so-called process engineers, is they try to optimize the fewest number of masks and the fewer number of steps that you can create this thing, create the wafer that you need. But they only have these few tools in their hand. Okay, so again, if they weren't so good, instead of having 50, I said this is an example of 50 masks, 50 plus masks. If they did it in a not so smart way, you could easily end up with 200 masks, and then this would cost you, instead of $300,000 to $500,000, it would cost you $2 million. So a lot of what they're doing is optimizing or minimizing, creating more efficient process.
Professor?
Yeah.
Are these wells like cube shapes? So they're also like rectangles on the width side, I guess, going in, because this is like a side view, right?
That's correct. Yep. So you're asking if, let's say, if I was going to draw, whoops, I'm really bad at this. So from the top, the wafer would look like this. From the side, we're saying it has this, but really, if you look at it, it's kind of got that look. And these are, like you're saying, they're like sitting in the silicon, but this is really a bad drawing. Is that kind of what you mean? They're like,
Yeah.
they have shapes on both top and bottom. Yeah.
Okay,
So
yeah, I just wanted to know if they're like square all the way through, or if they just were like cylinders where they're like round because the wafer's round.
Yeah, no, they look like, if I look at the top view, so here, as we'll see in the way the masks look, what you're creating as a designer is, again, I'm like, really, this is really, really gross, but you're creating a whole bunch of like rectangles. Okay, and then depending on the process, so let's say these rectangles represent areas of N plus for the wells. Okay, you have control over the X and Y dimensions of these N wells. But the process engineer has decided how deep these will be in the Z direction going into the wafer, if that makes sense. So again, you are, let's say if I look at this cross section, you are defining how big this well will be in this direction, but you have no control over when the guy puts the N plus, whether it looks like that or whether it looks like that. Because he's deciding how much implant, how the density of the amount of implanted energy.
So to change between the N type and the P type, would you use just a different wafer, or would you reorientate to reuse that, or not wafer, but different mask, sorry. Or would you like reorientate it or reuse a different mask to get like two different types? Because
Um,
obviously you don't want them on the same place, right? So,
yeah, but you might want them adjacent to each other. For example, in a case, you might want to have, N plus and then P plus wherever there is no N plus. Let's say you wanted that for whatever reason, which is a case you would want such a thing. So here you could use the same mask, but different photoresist to, like, some photoresists harden where there is light and some photoresists harden when there is no light. They're called light field and dark field photoresists. So you could use the same mask, but in one case, when you want to put the N plus, you can shield all this stuff and implant the N plus. And when you're done with that, you'd end up shielding this and putting P plus everywhere else. So you kind of use the same mask to get N plus and P plus, but then they would be directly adjacent to each other. So the answer is kind of all of the above, all the options you said, depending on what they're trying to do.
okay, thank you.
Sure. Let's see, what else do I want to say? Okay, so this stuff gets, what I want to say, let me just walk through here. So I think the upshot, or let's say summarize what I've tried to convey to you guys so far, is that everything happens on the top side of the silicon wafer. So you're coming from the top into the silicon, all the business end of it is at the very top. And what you have is the manufacturing plant has a few tools. They have implants, they have etch, they have lithographic patterning. This is for the silicon. So the transistors are all in the silicon. So all they have there is implant, etch, and oxide deposition, and the patterning of these patterns. That's all the tools they have in hand. And then on top of the silicon is the metallization. There's different layers of metallization to connect these transistors that you've created. And all the tools they have for there are oxide deposition, metal deposition, and lithography and etch. Okay, so what they're doing is they're using masks, they're using photoresist, but it's a multi-step process. So these wafers, I don't know if you guys, the video was at the beginning of the class, but the guy said it that, each wafer is going through 200 steps, and it's repeatedly these things are happening. You're depositing stuff, you're using lithography to pattern it, you're etching it, you're whatever. So then you just repeat, and you build layer by layer. You're building this material until the end process is, something like this, where you have, after all that's said and done, you've got NMOS and PMOS transistors and connectivity between them. But it's a bunch of these, they have very few tools, given what they're building. They're very sophisticated. I don't want to overstate the fact that they have few tools, but there's thermal steps, there's a bunch of stuff, but really when you break it down, it ends up being very few tools that they can adjust here and there. And so then they're trying to build something complicated. And as you can imagine, the other complication, which is very interesting, is so let's say you have 200 steps in how you're making these wafers. The 100th step better be compatible with the 5th step. Otherwise, the 100th step is going to damage what you built in the 5th step. And that typically ends up being like thermal cycles, because in between, I mentioned it a little bit in the photoresist, but all these processes, either during the process or after the process, so either to do the process or to clean up after the process, you tend to heat up the wafer. They just like these chemical processes, they like heat, whether again is to clean up after the process or to do it during the process. So you do your hottest, your early steps can be hot relatively, but your future processes have to be step by step less hot. Otherwise, they're going to affect, like if your 100th step is at a temperature that's going to mess around with your 5th step, you're in deep trouble. So just the thermal steps that this wafers have to go through as you're building up these devices tend to be very complicated, because you want to make sure they're not really interacting with each other, or if they are interacting with each other, you better make sure they interact in a way that's very predictable. Okay, so anyway, so I want to build that. So you go through these steps of the process, and as what you start with is you first start with building your your isolation layers. So again, you have this p-type substrate. Sometimes this epi, I didn't want to get this into too much into this, you actually grow, so this is your wafer. So this is your this would be like your very thick wafer, like 750 microns. Sometimes you grow just a very thin layer of epitaxial layer. Epi means on the surface, epitaxial. So just to tune your transistors, but then don't get too distracted by this. So the first thing you do is you pattern this wafer to basically you're etching into the silicon. These are the isolation layers between transistors. So this is really the only time you've etched through silicon. You've removed silicon to put isolation between your so your transistors will be sitting here and here, and you want them isolated from each other. And this is one of the few steps, because your etchants are so strong, you actually use with your lithography steps, you actually can, the photoresist isn't strong enough to stop this etching. So you actually first you put a silicon nitride layer, which is relatively pretty tough. You actually pattern that and you use that as the actual mask instead of the photoresist. So use the photoresist to pattern the silicon nitride and use that silicon nitride as a mask for your etch. And this is just because it's such a strong etch that it would just etch through the photoresist. So, but it won't etch through the silicon nitride. So silicon nitride ends up being the mask for this etching of the silicon. And then you remove the silicon nitride away and you deposit you fill these end up with these trenches here. So you end up filling these with oxide and end up being with isolation. So this is where these trenches will end up. Okay. And then basically you, after that, you mask out. So you mask out where you want your, mask out where you don't want your end wells with this photoresist, and you put down your end wells. Okay, then if you have P wells, you mask out everything else and you just put where the NMOS transistors are and you leave those where you want those P wells. Now, one thing you've done here in this step is below the nitride, you've deposited already the silicon dioxide for these gates. So you can see here, This is the oxide for the gates. So you're implanting through the gate oxide, which is okay. You're not really damaging it. You're sort of you're fixing the gate every once in a while with thermal steps. Okay. And so I was mentioning sometimes you use this P plus for the NMOS transistor to tune the device, and you're really tuning the threshold voltage of the device. And we'll see what that means about the threshold voltage, but this would allow you to adjust the threshold voltage. Okay, the next step is you put in the polysilicon gate. So you etch, again, you pattern that and etch it, so you end up with the polysilicon gate when you need it. Okay, and then you end up using the polysilicon gate as a mask so now you mask this region and you deposit N plus, and so this basically puts N plus directly underneath here for the source and drain, and you put P plus here, and you end up with P plus for the source and drain of the PMOS. So this step is called, so this is kind of a unique thing, and these are like some of the discoveries that they had problems with. So let me talk about that a little bit more. So, you know, when you have a, say, NMOS transistor, you have your silicon dioxide gate here. You have your, you have your polysilicon gate. And, you know, I just sort of drew the source and drain here and here. N plus P here, right? So I drew it like that, but and then, you know, okay, it's easy to draw like that, but how do you build that? So it's very, these mask steps, there's something you have to do with these. You have like 50 masks and you have 200 steps that are happening. Now, these all have to align with each other physically. So let's say I'm printing something on the wafer. The next thing I want to print on has to be like have physically match up right up to what I printed the last time. Okay, like this, if I was going to try to build this mask that created this N plus, so this mask that created this N plus, if I use this different mask for this, then this, these two masks better kiss up right up to each other. I mean, really kiss up next to each other. Otherwise, what you'd end up printing very easily is this. You would end up with the gate, with the polysilicon. And if you even had a little bit of misalignment, you could easily end up with this. Right? Then you ended up not, this mask that created this would just be slightly misaligned with this mask that created the polysilicon. And now you have a gap between your source and your gate. And as you'll see, this gap would mean that you could never turn on this transistor. This transistor would be dead on arrival because you would have no control over this region here. Okay, so this would be a non-working transistor. And you can imagine every layer is like that. If I was going to put a piece of metal here, you could easily end up in a situation that the piece of metal would end up here. Remember, you're talking about, these are 3 nanometer, 5 nanometer, I don't know, even big ones are 65 nanometer features that you're printing on. So these various masks or these various steps have to be really super well aligned with each other. And so there's still, though, some misalignment. I mean, you're talking about still, these are man-made mechanical stuff that sits next to each other. They do it very, very accurately, but there's still always some misalignment. There is, like, if I was gonna put a metal layer, draw that in blue, it could end up here, or maybe it's ends up slightly different over here. And as you'll see, there are these things called design rules. Which are these rules that the foundry gives you as a designer that says, hey, don't draw this thing too small, or don't draw this metal thing too small because I won't be able to print it. Or don't make it too wide compared to this polysilicon, otherwise it might hang off this ledge. I need to make this guy smaller than this guy, so even though this guy moves around a little bit, it'll still end up on the polysilicon, and so on and so forth. Every layer has these rules to make sure they can print it. Now, the one place where no matter what they do, it's an absolute death is this case. If the source and the drain don't end up exactly, and I mean exactly, aligned with the gate, you'll get a non-functioning transistor. So any movement this direction or this direction could mean that you either have a gap here, or you would end up having a gap on this side. So how do you solve this problem? This is a problem they were having very early on. So the way they solve this problem is why the polysilicon is used as the mask layer. So if you have, this is the silicon dioxide and the polysilicon sitting here. If you, using a combination of resist and the polysilicon itself, if you put resist, photoresist, if you put photoresist here, so let's say this is photoresist. And I put photoresist here. So this can move around back and forth a little bit with respect to this polysilicon. You don't really care. The important thing is right these edges. So now if I implant this guy with N+, the N+, the polysilicon makes sure that the N+ ends up exactly on this edge, because the polysilicon itself ends up them being the mask for the N+, and it makes sure that there's no N+ underneath it, and then it makes sure that the N+ is here. Now again, there could be some movement here because the photoresist isn't printed necessarily that accurately with the polysilicon, but you don't really care about this region here. That won't affect you much at all. It'll slightly change the area of the source and drain, but you're guaranteed to get a working transistor because the polysilicon itself is acting as a mask for the source and drain. So this was like a really big breakthrough in building these things, and it's called the self-aligned process. And that's why here you see that they deposit the polysilicon before they do the implants for the source and drain, exactly to get a self-alignment between, to make sure basically your transistors work. Okay, so after all that, after you've made this stuff here, at this point, you've got your polysilicon, you've got your gate, you've got your source and drains and contacts, etc. You've got your isolation. And now at this point here, you're done with your silicon. So you've processed everything after this point is stuff you put on top of the silicon. So everything here is implants into the silicon, etching of the silicon, those kind of things. And this, by this point, you've made already your transistors. Okay, so after this point, you're connecting your transistors by putting in oxides on top of your transistors, etching holes in there, and depositing metal here between your transistors. So here you'll start depositing metal lines. So this metal line here is connecting to the source. This metal line here is connecting the drains of the PMOS and the NMOS together, and so on and so forth. So you basically, everything, you go through a bunch of steps to build your transistors, and then and those are all, again, those are all in the silicon, and everything after that, all the connectivity ends up being above the silicon. Okay, so this is another, brings up another point, is that if you look at the silicon wafer, the transistors are in a so-called planar process. Meaning that the transistors are, they can only sit next to each other. You can't have a transistor sitting on top of another transistor. Okay, so you'll have NMOSFETs and PMOSFETs. They're all sitting on the surface of the silicon next to each other in a planar flat region. Okay, so the transistors are sitting next to each other. But as we'll see, the connections between the transistors, excuse me, guys, the connection between the transistors are in layers above the silicon. And in fact, you want them to be, those guys, you want multiple layers of metal and oxide, because you want this connectivity and you want complex connectivity. So that ends up being in sort of 3 dimensions. You have metal lines sitting in the same layers next to each other, but then you have metal lines in multiple layers sitting on top of each other as well, to be able to route these metallizations. Okay, so this is just a 3D perspective drawing. Maybe this goes to Tyler's question about what these things kind of look like. So this was probably what I should have come to, but you kind of see this. We've been looking at it from this direction, which is, the N plus and the gate. But if you look at it in a 3-dimensional way, you'll see that, this transistor has got a dimension in this dimension and in this dimension as well. So if we look at the different masks, so this is if you look at this is really zoomed into the individual transistors. Okay, so this is the drawing of a, how are we doing on time? Oh, sorry guys, let me just put this last thing, just to hopefully make it all come together. So this is what you'll end up with as a designer. This is what you would want to draw. So this would be an NMOS transistor, and we'll go into the details of this. This is the source and the drain. This is the connections to the source and the drain. This is the gate. This turns out to be the PMOS, source and drain of the PMOS, the gate, etc. And each one of these things is on these are what the different masks look like. So you're using the same poly mask to draw both the gates, so the N and the P. You're using the active, the well, etc., the metallization, and this is the cross section. Okay, guys, I'll stop there. Any questions? Yeah, I think this is the toughest one to do online. So hopefully this will be the I know this is really hard to do online, so hopefully you guys got it. Okay, guys, well, have a good long weekend, and I'll see you guys next week. Take care.
Thanks,
Thank you,
Professor.
Professor.
Take care.
Thank you, Professor.
Thanks.